So my topic's on putting design back into ESD, which is a little bit tongue-in-cheek, but hopefully I don't put too many noses out of joint as we go along through today. Are we ready to go? Yeah. Okay, cool. And we're recording it because there's a bunch of people over there that are going to get it. So feel free to ask questions as we go along, but I'll try and be really quick. Should be about 20 minutes worth, and maybe open it up towards the end. So I'm one of the co-founders of eTool, lifecycle assessment tool that we've built. So I'm going to start with what the definition of design is, which I think quite often gets lost in the world of what we do. Essentially, it's a specification of an object that has a series of goals or requirements that you've got to get to, and you're subject to a set of constraints. But that's essentially what design is. There's plenty of different definitions if you look up dictionaries and so on. But I reckon that's about as good as you're going to get when it comes to doing what we do, which is designing in the built form. And I think if you set off with what the definition of good design means, you start with an artist. Now, an artist sort of has almost no constraints. An artist basically just has a vision. Their constraint might be the size of the canvas that they have and the budget that they have they can afford on paint. But other than that, there's nothing. Their creative mind just gets to work and they create something that's beautiful. And their goal or their requirement was to create something either intrinsically beautiful or something that's going to spark interest or whatever. That was their goal, and the constraint was the size of the canvas and the paint they had, and away they go. Now, architects are pretty much the same. I mean, you've got a goal, which is to create a beautiful building that works, that people can function in and has a good outcome. So pretty much a similar concept. Now, engineers are the same. Everyone thinks that engineers aren't designers or architects, but we are. We have requirements, we have goals. You know, building has to stand up. So that's our goal, that's our requirement. And the constraints are budget, material use, and so on. And we have to hit those goals with that budget. So we're all designers, and in the perfect world, you have all of these designers working collaboratively with the client, and we all smile and we're all happy and we all hold hands and sing Kumbaya and we get a really, really good outcome. And that's the definition of good design. Thank you, Rick. Alex, how are you? Yeah, good. We'll get you a beer too while acting, mate. Oh, yeah. So that's the definition of good design. So I was going to give you two examples. The story of two designs. So I guess this is the first story, and I've changed the picture. It doesn't actually represent a real client, although that is a client. But this is a performance-based client. This is the client that comes to us and doesn't put any constraints other than I have a budget. It's like the artists. The only constraint is the size of the canvas. And all that client said when it came to ESD, I want a carbon neutral outcome. That was it. It's got to be low cost. So that was our constraint. So what did we do? Well, we went away and we plugged all the different options and opportunities for technologies and solutions in there, and they got a 7-star thermal performance, which is 1 star above business as usual, 1 star above building code compliance, which is 6 star. So a lot of ESD types would probably say that's not very good, 7 stars, not very flash, but that's what we did. Solar PV, solar hot water, a bunch of low embodied energy materials, and a few other bits and pieces, but essentially they got a carbon neutral outcome. So 100% improvement on business as usual, a house that's producing way more electricity than it's consuming. The additional capital outlay for that particular construction was about 10 grand. So the return on investment for the stuff we did is going to be about 5 years. So a pretty damn good outcome. The next example is the prescriptive-based client. So this is a client who says, I want it to be eco-friendly, and it must be 10-star. I must have 10 stars. I must have double glazed windows, and I want a roof garden, and it must be north-facing, and all these other things that go into this. That's not the exhaustive list. So basically, the design had been done for us. You've basically given the artist the canvas and the outline of the picture that they have to paint and told them what colours they have to use. So that's what we gave them. There was not much to it. We couldn't really do anything. Now, all of those things gave them a 15% improvement on business as usual. Cost them about 45 grand extra per unit. They got a lower yield because they had a roof garden, they couldn't fit an extra apartment up there. Return on investment was probably 25 years at worst. So there's two examples of two different clients and two different design approaches to ESD, environmentally sustainable design, prescriptive versus performance. So where did it go wrong? Well, being over-prescriptive in the design brief. You took the D out of ESD. There is no design. You've got an artist that's been told what colour paints they have to use and what size of canvases and what the outline of the drawing's going to be. You've got an architect that just has to build it like it's been spec'd. You've got an engineer that just basically ticks boxes at the end of the design and goes, okay, well, you've got a 15% improvement. Yeah, you've got your 10 stars. Yeah, cool. On we go. So you have no happy designers. You might have a happy client because they got the 10-star building, and we didn't sing Kumbaya and we didn't hold hands, and you got a pretty crap outcome at the end of the design. The other thing that goes terribly wrong there is that there's no performance-based target. So it was eco-friendly. I must have eco-friendly, but there was no, I want it to be carbon neutral, or I want it to be X kilograms of carbon per occupant per year saving. So there was no really tangible targets to hit. They were all sort of very prescriptive-based targets. So there are two massive things that go wrong in that style. The third thing that happens there is it generally gets bolted on at the end. It's a rating system. It's a let's design it all. You've already told us how to design it, from the architect to the engineer, and we'll just see how it performs. And we go, oh bugger, I wish we had done more of the design phase. So they're the three things that typically go wrong with that style of design. So I thought I'd take an analogy from a different industry. This is car manufacturing industry. So very similar approach to design though. You have a CEO. Now that's a terrible indication of what a CEO does, but essentially their requirement is to make money for the shareholders. You know, pretty much first and foremost, and that's okay. So how do they do that? Well, they sell lots of cars and they have a profit margin on the car. So their requirements or their goals, and we went back to that definition from Wiki, is cars per year and dollars per car, the profit margin on the car. And it's really easy. And then they say, okay, to the designer, design me something. Now the designer goes, oh yeah, wicked, I'm going to give you a really nice looking cool car. And so the marketing design requirement or goals is to have something that really looks cool. I'm really simplifying the car manufacturing, the car design industry down to some pretty basic formats, but you get my drift. The engineer goes, well, I'm going to get you a fuel economic car. I know what to do. Has anyone seen one of these? They're the coolest things. They come out of India, but the Australian government's blocking them with some crappy safety thing, but essentially they're made of plastic, like a surf ski. So, in a fully electric car, super light, but basically it's an engineer's energy efficient car. So if you went to an engineer, give me a car, the engineer goes, what's a car for? Oh, that's right, it's to get from someone from point A to point B. And they don't give a shit what it looks like. There's no status at all, there's no status symbol in that car because the engineer doesn't care about status symbol or anything. They've just gone, oh, I've got to get you from point A to point B. What's the lightest? Oh, okay, that's probably plastic. It doesn't matter if you scratch it. You know, if we run into another car, we just punch it back out and no one cares. So the car manufacturers hate it because apparently 50% of their profit comes from ongoing sales of parts. And there's not a lot of parts that you swap out on this thing because if you think you just pop it back out. Electric means there's bugger all maintenance and so on. Anyway, it's a genius car. So I went off on a tangent there, but there are sort of three sort of things that happen in the design of the car. And everyone's got a different idea, but the car industry generally gets this right. The CEO goes, I've got to sell lots of cars, and mate, no one's going to buy that piece of crap, so try something else. And they say to the marketing person, yeah, we're not going to get any profit margin out of that thing because it's going to cost us a fortune to build it. And they go round and round, and eventually they get something that works, and we end up with, you know, an example of, say, Nissan Leaf, which is going to be mass rolled out. So that's good design, and generally, a lot of industries get this right. So how do we get it back on track when it comes to the built form? Start by defining what your objectives are. So environmentally sustainable design objectives are. And they're going to be water, they're going to be carbon. Mark, you were talking about this just before. You sit down with your clients and say, what is it you actually want to achieve with this thing? And you list them all. Put them all up on the whiteboard, get your sticky notes out and whatever, and put names to them. And then decide whether these things can be quantified. You know, which ones out of these can you actually put a number to? And obviously carbon you can. You know, it's kilograms of carbon dioxide equivalent. That's bang, you've got one. Water, yeah, definitely. We've got litres of water kilolitres of potable water. Maybe we've got one. Affordability, well, that's just dollars. Yeah, we can put a number on these things. So put numbers on the things you can put numbers on. And then once you've got numbers to them, you've got to work out how to quantify them. So this is, I guess, where we come into it. We use a methodology called life cycle assessment, which I think a few of you might be familiar with, those that we've already worked with. Essentially, another name for it's cradle to cradle. So you're following a product from raw extraction of raw material all the way through its material life cycle back into the food chain. If it's cradle to grade, it's getting thrown in the bin. It's cradle to cradle, it goes back in now. Every product has a life cycle, and a building's no different. Typically, people think life cycle assessment's about, oh, I'll look at a beer and I'll do a life cycle assessment of a beer, or they'll look at a brick and they do. We've decided to take that methodology and apply it to buildings, and it's really the only way you get a true understanding of what the genuine environmental impacts of a building is going to be, is through a full life cycle assessment. So I guess when you look at a building, you start with, say, your materials. And if we pick something like iron ore, it's going to start as iron ore in the ground up in Pilbara. You're going to dig it out of the ground. There's going to be carbon energy associated with that digging process. You're going to process it there. You're going to transport it. It ends up getting to China and goes to a factory where they turn it into a building material. From that building material, it's going to get transported again. It'll probably go back on a boat, back to Freo, into a truck, maybe to a holding yard, then onto a smaller truck, and then eventually to a building site. So you have that transport. And then when it gets to the building site, you have to glue it all together, so there's a bunch of energy and carbon associated with gluing the thing together into a building, and then we operate it. So this is typically where we've always focused when it comes to ESD. We always look about, okay, well, how do we get good thermal performance? How do we build hot water into there? How do we build lights and lifts and car park vents and solar PV? And it's typically the biggest component of your carbon impact, and that's your operational stuff. But you also have things like maintenance. So paint's a really good example. Typical, say, residential building, maybe 0.2% of the total carbon footprint when you build it's wrapped up in the paint. But let's say you paint it every 10 years, and that thing lasts 100 years. You're going to paint it 10 times. 0.2 might turn into 2, or 1.8, depending on how you do the numbers. So suddenly your recurring really stacks up. Things like carpets, which is great that we don't have carpets here. We love raw finishes. And then you obviously have to dispose of that thing. Hopefully, rather than going to landfill, it gets recycled and put back into the food chain, and away you go again. So that's the cradle-to-cradle understanding of how a building operates and the full life cycle of a building. Now, the other really important thing with life cycle assessment, and a lot of people forget this, is they think, oh yeah, I've done my materials, I've calculated the embodied energy, and then I just gave my operational energy, I'm done. Well, that's only half the picture. In fact, functional units probably as important, if not more important, than the cradle to cradle. And what a functional unit is engineering nerd tech speak, but functional unit is as it sounds. You actually stop at the beginning and ask what's the function of this product. So coffee machine's a really good analogy. So you have coffee machine on your left here, and this comes from Target. It's made of extruded plastic. Not a lot of energy and carbon associated with making anything. Then you have the one on the right, which is the handmade stainless steel jobby from Italy. Huge amount of carbon and energy associated with building this thing. This one on the left, so if you looked at it like that, you go, oh, let's buy the one on the left, but this is much better, lower embodied carbon. However, you didn't stop to ask what the function was. Now, this one here might be lucky to punch out, I don't know, 2 cups of coffee a week sitting at home in your lovely home kitchen. Gets to almost the warranty, probably just over the warranty period. And this little knobby thing here cracks and falls off and you bug it and you're like, oh, okay, well, I'll just go and buy another one. So you throw that in the bin. So it might have been lucky to punch out 100 cups of coffee. This one here probably is punching out, sitting in a cafe somewhere, is probably punching out 1,000 cups of coffee a day. And then at the end of the year, you do a service, does another 100,000 cups of coffee in a year. Then at the 3rd year, there's a service contract. Someone comes out and fixes a few things and away you go again. So if you wanted to really understand which is more sustainable, we have to understand what the kilogram, if you're interested in carbon, this is because you might be interested in the water or whatever, but if you're interested in carbon, it's kilograms of carbon per cup of coffee. And that gives you a fair comparison between those two things. And that's the important thing with life cycle assessment, is you're not just doing a cradle-to-cradle analysis, but you're actually stopping and asking what the function of the product is before you go and design something. because if you didn't, you'd probably design this one, thinking that's the way to go. So functional units are really, really important, and they apply just as much to a building. For instance, this building here might have got a 10-star what's a jiggy rating, recycled materials, LED whiz-bang tube lights in it, beautiful cross-flow ventilation, high fly ash concrete, big solar PV system on the roof, and there's one person working in it. And you pat yourself on your back and go, yeah, we've got a good sustainable outcome here. This one might be just business as usual. That might be an old building like this. There's nothing special about it except you've got hundreds more people working on it. So the carbon impact per person per year, if it's residential, you generally work an occupant. If it was office space, you're probably working on desks or workstations. If it was a warehouse, you'd probably work on metres cubed or whatever. That's how you compare these two things, and that's how you really identify which one's sustainable and which one's not. So that's how you quantify stuff. So bringing it back to the original question, which was getting us back on track, the things that you can quantify, you quantify. And you put a life cycle assessment approach on it and you create a functional unit. So if it's carbon, you put the target. I want it to be carbon neutral, which is really easy. So instead of XX, it's just 0 kilograms of carbon per occupant per year. You might go, like, I want a 50% improvement. So you go, what's a normal building? It's a tonne of carbon per occupant per year. So we're aiming at 500 kilograms of carbon per occupant per year. Same thing for water. X kilolitres of potable water per person per year. Now, the funny thing is, the water guys have been doing this forever. They've always sort of had nice, tangible targets for water saving. It's just that the energy and the carbon guys are just catching up, I think, really, in doing that for LCA. It might be things like land use or clearing of natural vegetation or rainforests, and you say, well, we're going to allow X number of metres squared of rainforest clearing per person per year, or whatever it is. So these are the tangible, quantifiable things. An interesting point to make though, this definitely doesn't define your design. It's not saying, right, you now must design according to these. They're only there to help inform the design. So as an architect or a designer, you're sitting there going, oh, shit, I've got to try and hit these targets. What sort of things should I be doing to hit those targets? How do I get there? And that's the important bit here with the quantifiable stuff. Actually, I'll go back a slide. There's a bunch of things you can't quantify, and I think maybe I'm jumping ahead of myself, but there's a bunch of things you can't quantify. And they're the things like community development, and a lot of social-based things that you can't put a figure on. And one thing we always give people crap about is putting bike racks in, because you get points for bike racks. And if you looked at the kilogram saving of carbon per occupant per year for a bike rack in a big high-rise building, it's a complete waste of space. You'd be far better off putting more people and operating more people in that building. But there's a massive flow on social benefit for having bike racks and having people riding, you get community development, you get healthy people. So again, you can't say this is the be-all and end-all. It doesn't lock your design in, and that's not the only thing that should inform your design. There's a bunch of other social-based stuff that's really, really important. So a very quick summary of ESD tools. That's definitely not an exhaustive list, and there's a bunch more than that. A lot of them are having a crack at bringing functional units and life cycle assessment into what they're doing. Some are more successful at it than others. But I think they all see the writing on the wall. That's what they're going to do. This is way too small for, I assume, you guys to see. And it's a very, very rough, quick summary of different systems out there that are used as ESD tools, so to speak. And I've put a bunch of, so these are different tools. I've put a bunch of different columns. You've got different scales, so whether it can be used on a residential or a $20 million job or whatever. Different project types that you could use it in, different regions that they're available in, whether they're prescriptive-based design tools or they're performance-based design tools. I pick carbon as an indicator of how much of the carbon of the building do they actually look at. Are they LCA-based? Obviously we've got a pretty big bias towards life cycle assessment. And whether we feel they're rating or are they design tools. So I'm going to quickly go through this, and you could have probably put 50 more columns there, to be honest, for different things that you should be looking for when you're talking ESD, and we could probably have 1,000 more of these. This is just infinite, and this is very rough. I'm sure some of the guys that do this for a living will pull me up on a fair bit of this, but essentially, looking at Green Star, you're talking, maybe $20 million plus projects. Anything smaller than that's pretty hard to make it work financially. You do a Green Star equivalency, obviously. Projects that they work on, commercial, multi-res, community. It's all in Australia. Now the prescriptive and performance-based, they're very prescriptive. So less so much of the pure performance-based targets in those. Percentage of carbon, they do a pretty good job. They generally take out about 80% of the carbon, or they're looking at 80% of the carbon footprint of the building. They haven't got life cycle assessment and materials in there yet properly, so they're missing a lot. Is it life cycle assessment based? No. Do they look at functional units? A little bit. So in our opinion, it's a rating tool. It's there so that you can do all your design work and then plug it in and go, what did we get? Oh shit, we're not there yet, let's go back again and then we'll fix something and check it again and see what we've got. So that's the difference. Now LEED and BREEAM are pretty similar. They're sort of the equivalents that you find in the UK and the US. Living Building Challenge, this is a really cool one that's come out of the US. Basically, very cheeky. Basically, they said, right, the best building you can get in LEED, that's the worst building that will rate when it comes to Living Building Challenge. They had a pretty cool graph where they had sort of, this is zero environmental impact, and this was the LEED building coming up, and a platinum rated building is zero impact in LEED, and then you move into the Living Building Challenge, and their idea is that buildings should have positive impacts on the environment and society. So that's their goal, and it's actually a really, really cool thing. They do have life cycle assessment to a certain degree. You do have to understand the embodied impacts of the materials that you're using in the design overall, which is really cool. And they tackle smaller budget buildings, typically, and they do everything from commercial to multi-res and community. And it's globally available, it's globally applicable. So that's another one. But it still is a rating tool. It's something that you have to do with your design work, and then you plug it in there and go, how did we go? Okay, yeah, we've hit that target, or we've hit those points. Okay, or haven't, all right, what do we do? We've got to change things here and then put it back in. Oh, did we hit it? Yep, we've hit it. Okay, away we go. The One Planet Challenge is another one. This is a really cool one. They came out of the UK, and much smaller scale. You can do from sort of 1 million upwards. Commercial, multi-residential, community type stuff. It's much more of a holistic tool. I don't have time to go into all the details of it, but and far less prescriptive. Both of these two are far less prescriptive. They say things like, I don't care how you get a carbon neutral outcome, just as long as you do it. So you can use a combination of different technologies and so on, and it's not so much of a point scoring exercise as a, let's see what the performance of your design was, and then decide whether you've got the points. So, and they tackle a lot more carbon, or a lot more of the environmental impacts. They understand embodied materials, embodied carbon materials and so on. So partially LCA based and less so of a rating tool and more helpful in the design phase of your buildings. Now, this is another one. This is Neighbours. This is a government-based tool. Can be used in much smaller buildings, I guess, than your Green Star. Generally orientated toward commercial buildings. Totally non-prescriptive. They don't care. They don't care whether you've got double glazed windows or tri-generation or solar passive design or solar PV. Basically all they've got is a set of numbers that they say, well, how much energy are you really consuming? So they come in after the fact that you've built something and go, show me your energy bills. And if your energy bills are low enough per square metre or per occupant, then you get a certain star rating. So that's a really performance-based spec. It's got nothing to do with scoring points here. That's purely about numbers. And it tackles a fair chunk of the carbon element of a building because it actually looks at the energy bill rather than your design. So that's a really, really effective way of rating a building. The only problem is it's not that handy in actually analysing the design at the beginning and say, how is this going to perform? So a really good list. It's very performance-based, but not particularly design-orientated. NatHERS, that's a residential tool. That's for looking at houses, looking at renovations. So people use that for $100,000 programs. It's only residential. It's Australia. Again, it's not prescriptive. Basically, what it looks at is the energy consumption for the heating and cooling, or your thermal performance of the building. And it again says, I don't care how you do it. You might use crossflow, you might use thermal mass, you might use insulation, or a combination of all these things to achieve it. So it's not saying you tick boxes for putting these things in there. You just have to model it according to the software to find out how it goes. So definitely a performance-based tool, but unfortunately it only deals with your heating and cooling, which really in a modern building is going to be somewhere around the order of 15% improvement if you've got a 10-star building over what you now have to build, which is a 6-star. So a great idea, but not tackling it everything. And then you have huge amounts of other tools. There's a lot of local government requirements, and they will come up with different ways of assessing buildings for their sustainability, and typically they are built around a lot of these things. They've got, you know, equivalencies to some of this stuff. They'll pick bits out of NatHERS and they'll cobble things together. And generally on the whole they get buildings going in the right direction, but typically quite prescriptive and less performance based. So look, there's a very, very rough summary. So I think from there we say, well, what is a design tool? And number one, it has to be performance based, not prescriptive based. So it can't be that, if you've got a genuine design tool, remember design was about not telling people what the colour of the paint has to be, it's about saying the goal is an energy efficient building. We'll leave it to you as a designer, an architect, an engineer to get it there. So a design tool shouldn't be prescriptive, it should be performance based. It's really important. It needs to consider everything. I will draw the boundary as far as you can. So, in our eyes, that's cradle to cradle. You're basically looking at everything then, and yes, we are biased to LCA, but it's what we believe in. Because if you don't, if you just take piecemeal and say, all right, it's all about solar passive design, or it's all about recycled materials, you're going to miss stuff. You're going to miss a huge amount. There you go. So you've got to look at everything, and you've got to look at it all at the same time, because what often happens is you might change something in a material, but it's going to impact your thermal performance. So you might have a positive impact in your materials, but you have a negative impact in the thermal performance. And if you've got a system that just says, oh, you must have recycled material, go, all right, we use recycled material, but you didn't stop to see what that does to the thermal performance. Well, you tick your box and away you go, you can have some really perverse outcomes. So it's really important to look at it all together. And finally, really, really important to include a functional unit, which is what I was describing before, like the kilograms of carbon per occupant per year. Because again, if you don't, you might have this incredible building that's zero carbon theoretically, and you have this huge glass foyer out the front that the security guard stands in, and you've got, you pat yourself on the back, go, carbon neutral building. But you've got this huge space that's being air conditioned, all this glass, and all it's doing is housing a security guard. So functional units really, really important to include in what you do. I think side elements to what makes a good design tool, it's got to be compatible with the design process. So it's got to be something that the client, the architect, the engineer, they can all sit down together with this tool or this concept and work through that whiteboard exercise and pin things up and create objectives and actually do stuff with it and actually inform the design. So it needs to have fast feedback. So you go, oh, what? Okay, we're in the design, we haven't even drawn it yet. What happens if we add another level? What's that going to do to my carbon footprint? Now, a lot of those other tools you mentioned, you've got Buckley's chance of understanding what your carbon footprint is going to do by adding a new roof or a new level. But if you don't at the design stage, you kind of knack it because you'll get a completely done building and then you'll go and rate it. So it has to have very fast feedback. It has to be very user-friendly. You've got to be able to extract that design data really quickly because, again, if you can't, it's going to cost too much. And people aren't going to do it. They're going to go, oh, well, we'll try this and hopefully when we get to rate it, it'll do okay. And then generally, again, you're pretty stuck and you end up bolting things onto your building to try and make it sustainable. So really important that it's user-friendly and cost-effective. It's got to be accurate too. And this is where it gets really tricky because it doesn't matter how smart you are, you build a bit of software, you build a tool, you're going to have to put boundaries in it, you're going to have to put assumptions, you're going to have to put algorithms, and they all have limitations, and sometimes you get it wrong. But we work on this premise that it's better to be vaguely right than precisely wrong. And what we mean by that is that you're better off doing it and finding out what the rough numbers are than pretending it's not important and doing a really, really stupid thing with your design. And I think most modelling software is the same, whether it's something that, like a NatHERS program, or a thermal performance tool that sort of tries to understand how your building's going to operate heating and cooling wise. They all have boundaries and limitations, but generally on the whole they'll get you a better outcome if you use them than if you don't use them. So there's sort of what we say is it makes a good design tool. So in summary, set performance-based targets for things that you can quantify. So that's your carbon, your water, your energy, daylight, fresh air, those sorts of things that you can actually quantify. Start by quantifying them and start by putting a performance-based target on them for your designers to work to. Some of the things that can't be quantified, so the more social-based stuff, understand what they are and say, yeah, look, we can't put a dollar figure, we can't put a carbon figure on people riding bikes, but it's really, really important. So those things go in as your qualitative, prescriptive-based measures for a good building design. And don't mix the two. And I've seen this happen where someone goes, oh yeah, we're putting a bike rack in because it's going to save carbon, that's why we're doing it. And you go, okay, rightio. And then a savvy developer goes, can you do me a calculation of how much carbon this bike rack's going to save? And you do the number and it's like, it's not saving any carbon. Good, let's get rid of the freaking thing. And the person who wanted the bike rack hasn't got a leg to stand on because their argument was about carbon. Whereas if they'd said, no, our argument's actually about the social-based element, it's about community development, it's about having healthy work staff, then it will hang in there. So don't mix the two. You know, don't try and disguise one as something that it's not really. Try and put the real numbers too. Provide guidance and assistance. Don't hit people over the head with these things and say you must have this number, you must have these things in the building. Set them as performance-based targets, but be prepared to be flexible because some things might work some places and not others. And let the designers design again. That's what we really want. We want clients, we want government, we want everybody to let us be designers again, be it an architect, an engineer, a construction manager. That's what we do. We spent however long at university or TAFE to learn how to do these things. And if you want a good outcome, the best way to do that is to let us what we do what we do best, which is be designers. And that's the end of the presentation.
Awesome.